Hey guys, we're recording. Stop talking. Thank you. Great. All right, and Ryan, can you put that? Yeah, whatever that's up. All right. What I want to do is actually I want to finish off the notes for part 2. I feel more comfortable we do that. I'm not going to do part 3 notes. So basically, we've done 3 days. Parts 1 and 2 spread out over 3 days. I do feel I could probably do all part 3 on Wednesday. Now sophomores are gone for the retreat, so I'm still going to do a lesson. So you are responsible for the sophomores to watch that. When we come back on the 8th, we'll do part 4 of the notes. Then we'll review, I believe. And I think the plan is to have the test on the 12th or the 15th. Let me take a quick gander here, what I had anticipated. Yeah, we're going to keep it on Friday at 12, the test, because I don't want us to fall behind, because when we come back from break, time is incredibly limited, and I do need a lot of time in chapter 3. Also, we do pay for SJTI as well the week after. So, and also there's gonna be APs coming up. I know a lot of you guys have APs. You're gonna be gone often. So I think it's best that we just keep the test on April 12th. So I do feel I can get part 3 of the notes done by Wednesday. Come back, we'll do part 4 of the notes. Have a day review on the 10th, test on the 12th. Okay, that's the plan. So anyway, the homework I'll talk about at the end of class if we have time. I will actually wind up making an answer key for this because I think you guys do need it. Because I just realized that you guys don't have answer keys for these. Am I having the binders here from Lucky, from Miss Jones? Maybe she's her handwriting's really nice, better than mine. So if I do, great. Not, I'll just make one. So anyway, so let's pick it up from page 3, part 2 notes, and let's finish this off today. Okay, finish this off today. Homework review, and then also the new homework will be. The new homework is going to be the rest of handout B and section A of the handout 3 or handout C. Sorry, that makes sense. Okay. Yes. That'll be the homework due for Wednesday. Yes. Oh, your tests, I have graded them. They're in Schoology. I'll go over if you have any specific questions. I know some of the grades were not great, some were good. But don't worry, that was our hardest test of the year. They're not going to be any harder than that. Okay, let's go, guys. All right, F of 2. So which function, guys, quiet? What do you guys think of F of 2? It's a trick question. Page 3. Yeah, why not?
Because it's not
right. Guys, quiet, please. Guys, I need you quiet. Thank you. Undefined because x equals 2 is not part of domain. Okay. It's not part of the domain. So yeah, you don't have it. However, this is a left-hand limit that has a right-hand limit, and that right there is a two-sided limit. We're going to investigate each of those 3 right now. So for part B, what I'm going to do is plug 2 into the left side. So I'm going to plug 2 into this one here, right? Because that's approaching 2 from the left. So that's going to be 2 plus 1, or just 3. Does that make sense, guys? Why I chose because I'm putting 2 to the left. But for C, I chose 2 from the right, so I'm going to use the second function, which will be 2 squared minus 2, will just be 2 again. Sorry, not again. What I meant, just 2. This one does not exist. Yeah, because LHL does not equal to RHL. Right. That one does not exist. Okay, so we're cool with A, B, C, D. So F of 2 didn't exist, but it doesn't matter for limit's sake. You just got to look at the left-hand limit, look at the right-hand limit, and make sure if a two-side limit does exist, that the left-hand limit equals the right-hand limit. Fortunately, it does not. So you can say D and E for part D. Now, F of 4 does exist. What's that going to be? Just 3 straight up, right? But from the left side, let me change colors for a bit of contrast. LHL, RHL, Two-side limit. So you're approaching 4 from the left side. That should be 4 squared minus 2, which is 14, I think. RHL would be this. We already know that already. That'd be 3. And again, that does not exist because the LHL does not equal to RHL. All right, we're okay with that? We're good? So that's how you deal with limits of piecewise functions, and the rest of the handout B deals with that. So it's not that hard. Just have to be mindful. Like again, if you're approaching from the left, use the right equation. If you're approaching from the right, use the right equation. And in order for the two-side limit to exist, the LHL must equal to RHL, and then of course it's gonna be that value. And f of 2, f of 4, whatever, has no bearing on limits. It's just you look at the piecewise function at that point, or I mean look at it for limits also, but you just plug it in into whatever expression it satisfies for the condition next to it. So we're good? Okay, let's move on to example 5. So for example 5, there's 2 parts, I believe. Yes. So let's write this as piecewise functions first. Here's how you do as a piecewise function. I'm going to do a little work off to the side here. Okay. And x equals 3, we just can't have a definition for it. We just really don't know which one to go with. It's not very clear. So you write as a piecewise function look like this. Um, 1 and -1. You guys okay with that? Right? Because remember, this right here is 2 different things. When the inside is positive, it's x minus 2, and inside is negative. In order to guarantee a still a positive result, we have to flip the x minus 2 make it 3 minus x when x is less than 3. Catherine, good? Yeah, exactly. Right. Exactly. So when you're asked to find the left-hand limits and the right-hand limits, that's easy. Now, I am going to ask you guys to be very formal when you write it. You have to write x approaches 3, and you got to do a superscript like that. We'll call it f of x, just whatever. Even though we didn't define f of x, we know what it means. So from the left side, it's -1. From the right side, so you do 3 and do a plus symbol as your superscript. That's 1. So obviously, this limit does not exist because the LHL is not equal to RHL. We're good? Yeah? Cool. All right. Let's keep moving. Okay, so here we're asked to find the limit. Again, we're going to write piecewise form. So now we're getting some really wicked stuff. This is getting to the weeds here. All right. So we'll call this f of x, right? Guys, quiet, please. Thank you. All right. So 1 over x plus 2 plus x squared when x is greater than -2, or 1 over negative parentheses x plus 2, or you do negative x minus 2, I don't care, when x is less than -2. Because when x is less than -2, you want to guarantee still a positive result for the denominator, or the absolute value expression. Okay. What do I need to do next? Give me a sec here. Why am I at a loss? Give me one sec. Oh, I should actually combine these, I think. Yeah. Hold on. I'm a little lost here. Let's just combine it. Let me write it again. Okay. So I'll do this over here. 1 over x plus 2 plus x squared it's all right, no worries. So it should be x cubed plus 2x squared I wonder if that's a factor. I don't know. Okay, guys, quiet. You got -1 over x plus 2. Again, same thing. That's x cubed oh boy. Let me think here. If you're approaching from the left side, I'm a little lost here. Let me do synthetic division to see if any of these come out clean. Don't copy this down, guys. I'm just doing this for myself. No. No. Yeah, I just combined the fractions, but I'm not sure if that really helps. Yeah, I don't think the limit's going to exist. Yeah. Yeah, go ahead. Oh, you want the negative counterpart because x is less. I'm making x less than -2. What was that? You want to guarantee the same result, right? That's all. I think in this case, guys, quiet please. I think what's happening. Yeah, let's look at it graphically, guys, because I'm stuck. So when you're stuck, that's okay. Let's just look at it graphically. Because algebraically, I don't think I can get anywhere with this. So let me go to Desmos. Here we go. Okay. So y equals 1 over x plus 2 plus x raised to the second power. Okay. So clearly it's going towards negative infinity. If I put a negative out in front, so let me copy and paste. Put a negative out in front. So it's pretty clear they're both going towards negative infinity on either side. So the left-hand limit is negative infinity. The right-hand limit is also negative infinity. So the limit of f of x as x approaches -2 is negative infinity, or DNE technically, because we don't know what that is. So I'd say approach. Yeah, I'd say approach graphically. Yeah, that's how I'd approach that one, because I was trying also to do that one analytically. So yeah. So sorry I was a little stuck there. I should have been mindful about that. Okay. We're okay with that? Mm-hmm. Oh, wait 1 sec. Hold on. I think I made a mistake somewhere. My left hand, the blue, shoot. Wait 1 sec. They're both positive infinity. My bad. They're both positive infinity because the blue is the left-hand limit. Yeah, so my bad. They're both positive infinity. My apologies. Yeah, think about it. The blue, let me turn this off. Yeah, as I get closer to -2 from the left side, that's approaching positive infinity. If I approach the red, that's a top function. So that's going to be my right-hand limit. That's also approaching positive. So my apologies, I looked at it wrong. Should be positive infinity for this one. So my apologies. Right, exactly. Right. Okay, let's keep moving, guys. I know I'll do the next one, I swear. All right, okay. Yes, Ryan? Yeah, go, yeah. Ryan, go ahead.
Just wondering, like, for these ones, how would we know when we need to like solve it through a piecewise versus regular?
I'll tell you. I'll instruct you. I'll say like, hey, you're like draw the graph. Well, try to piecewise draw the graph and then make a thing. Yeah, make a determination after that. Now here, actually, this I know what to do. Here's what you do. This is a very common one. So you're gonna write like this first. How does inside factor, guys? Yeah, there we go. And when you square root, I'm not sure if you guys know this, when you square roots, it's absolute value. That's something you may not know, but when you square root, it has to, because you have to guarantee a positive answer, a positive outcome. Because remember, square roots always have positive y values, right? Unless you have a negative out in front as a transformation. So now as a piecewise function, it's going to be this. X plus 6. Should x be bigger than -6? Or x minus x plus 6. Should x be less than -6? So that's going to be 2x plus 6 or just -6. Okay, so that's pretty obvious. What do you guys think part B is going to be? Part B has to use that one, right? So that's just infinity. Because you're plugging in 2x plus 6. But for part C, what do you guys think part C is going to be? Just -6, good. Yeah. Yeah. And that's how you have to write it. So this one we can do analytically because we have to realize square root of a square comes out as absolute value to guarantee a positive result. And then the absolute value can be written as a piecewise function. -6 is kind of like the pivot point or the vertex. When x is bigger than -6, the expression is x plus 6, right? Because it's positive. But if it's negative, you have to change the sign in front. So, okay, questions? No? All right. Okay, continuity. This is a big one. This kind of defines a lot of the first semester of college level calculus AB. Okay. Visually speaking, it's basically kind of like a pen or pencil test. If you have to lift your pencil off the paper or pen off the paper, or the marker you have to lift it off the board, it's not continuous. There are some conditions for continuity, which we'll talk about just a little bit. But right now, like if you look at this one here, that's continuous. That's not continuous. Because A and B is nice and smooth, right? From A to B for the first one. But from A to B for the second one, there's a jump. Well, not jump, but a removable discontinuity. We actually call this a removable or a point discontinuity. Does that make sense? For these here, not continuous, not continuous, not continuous. We call this a jump. We call this an infinite. Okay, I can't spell. Infinite, there we go. And this is oscillating. We just don't like, for example, this could be like sine of 1 over x. It's not continuous at it's not continuous at 0, right? Because it's not going to be defined there. But what's happening is we get close to it, it's still stable. So that's what I call oscillating. But the whole point is that there's no value at 0 for x. So that's what this graph represents. Or cosine. Here, obviously, you can't equal whatever this is. C, like that's the vertical. Here, it is defined, but we see that the left right now is not the same, right? And then for up above, the removed continuity, the limit does exist, the point does exist, but they're not the same thing. And so basically, let's focus on the second, third, and fourth graphs, because that's going to help us understand the definition of continuity. We're going to define continuity on the next page. Question, are you?
So it's not defined that's oscillating, if that makes it not
Because 0 is not defined.
Okay, so
yeah. So this is the big moment, because this is really what, and you have to really cite these 3 things for continuity. So on the AP exam, which you guys are not going to take for another year for this subject, you do have to cite these 3 things, because even though you guys will be, most of you guys, or I think everyone should be doing BC, the problem is not the problem, but the thing is that you're expected to do AB stuff as well. And you don't really cover this stuff when you start BC in the fall. So you kind of have to go back and look back at your stuff you did as a spring of this year when you're studying for the AP exam this time next year. Because they do ask, because there's a lot of overlap between AB and BC exams. So here are the definitions. Actually, I'm going to type as text boxes. F of C exists. The limit as x approaches C exists, meaning the LHL equals RHL. The limit of fx, sorry. That's what you say there. And lastly, this one here, f of c equals the limit inside the interval you're looking at. So like, great question, actually, I should have defined that. So say this is A, and this is B, and you got like a funky curve like this, and C would be in the interior. That's what's meant by that.
Every point.
Exactly, right. And so basically you have to guarantee that any point in the interior is going to satisfy each of these 3 things. So like say that like 1 and 4, let's say. So like that's like 3.99, whatever. You gotta make sure F of C exists, the limit as X close to that number exists, and F of C doesn't equal that number as well. Obviously, because I typed it up, I don't have the capability of writing this in a more formal way. But formally write like this or shorthand notation. This right here, same thing, right? Right? Okay. Okay. Okay, domain. Let's do that down here. Guys, what's the domain for this one? Guys, help me out. Yep. Negative 5 is included. Okay, so part B. And the graph, by the way, let's do the graph really quickly. It's negative 5 and 1. We plug in negative 4, I get 2. Plug in negative 1, I get 3, I think. Plug in 4, I get 4. Okay. So show that f is continuous at x equals negative 1. So basically f of negative 1 exists. Check. The limit as x approaches negative 1 exists. Check. And f of negative 1, that's how you do it formally. You have to go through these 3 steps or these 3 conditions. check. And if you actually want to solve it, yeah, fine. What's f of -1, guys? 3. What's the LHL here? 3. And RHL is 3. So the limit is 3. And 3 equals 3.
That's what it looked for the AP exam. Just response, look for this. You gotta say all those things. You can't, no shortcuts.
You guys state it like that. F -1 exists. Was x plus -1 if x exists? F -1 equals limit x approach -1 if fx is true. And also, state the values. That's how you have to go through it. Now, in this case, let's look at part C. This is where it gets a little tricky, guys, for part C. I'll explain in a sec. Okay, clear? Clear? Okay, great. So, for part C, f -5 equals 1. So that exists. The limit. Now, this is the part that's tricky. Correct. So there's an exception here. That's the exception.
Little dialog box. The appropriate one-side limit is okay for continuity at the endpoint of the domain. Yes, there's no LHL.
But just use RHL. That's all. And then f -5 equals the limit so we're good on that? Yeah, you go, it's fine. Okay, find any points of discontinuity. There actually aren't any. I mean, of course, x can't be less than -5. Because not defined there. But is it a continuous function? The answer is yes, on its domain. On the domain of the function itself.
It is continuous, right? The domain from -5 can be included. Yes, it is. But you have to be kind of specifically on its domain. There's some cases where they won't see it.
Usually there'll be like piecewise functions, like we'll have a domain and we're deliberately not continuous there. But on its domain, it is. So that's just kind of one, kind of like the fine print. Like you have to make sure that you say that. Yeah, it's on its domain. And fine points is continuity. Of course, x can't be less than -5 because it's not defined there. So you could say that, I suppose. But it's not part of the domain anyway. All right. So again, the domain we got, -1, just go through the 3 conditions. See, we did this 3 conditions as well, but for the second condition, we just use the appropriate one-side limit. For D, points of discontinuity are any points that don't satisfy any of those 3 conditions. In this case, just anything that's not defined, which is less than -5. And as a continuous, we could say, yes, it is, but on its domain. Okay. Yeah, and see here, on its domain, they kind of specify that up above as well. Yeah, and look at the definition down below. A function is continuous in an interval. Now, sometimes they might be asking a question.
Like here, they give you a function and they specify a certain interval. We'll talk about the difference here. But the function itself is continuous. If only if it's continuous on every domain. But if you specify a certain interval, is it going to be continuous? Well, you got to make sure it satisfies all 3 conditions if you're giving a specific interval.
So let's talk about that difference on example 10. And then we'll do examples 11 and 12, then we're done. I won't go any further. And then I'll tell you what your homework is so you guys can get a head start if you want. So 1/x, you guys know this, right? This is why we spent all those years in Algebra 2 trig honors and early in this class and even in middle school. You know, we really want you gotta be well versed. You gotta be able to do these graphs like that really fast, right? You gotta do really, really quick. Can't think too long and hard about them. Okay, over all real numbers, is this continuous? No. No, because at x equals 0, we have an infinite discontinuity, right? Because does the limit exist as x approaches 0? No. One's going towards anything, one's going towards positive infinity. So no, it doesn't exist. So basically then condition 2 fails, right? Condition 3, I guess you could say fails too. Remember, condition 2's limit has to exist. So that completely fails. Now, what is the domain here though? Yeah, everything but 0. So is this a continuous function? Yes, on its domain. On its domain, this is considered a continuous function. On its domain.
Because zero's not part of our domain. So we'll never investigate it. We'll investigate also never zero.
Yeah, good.
In general, like if it doesn't like specify the domain thing, can we say like a continuous function?
Yeah, totally. Yes. Like tangent, for example, that is continuous on its domain. Like every, pi over 2, 3 pi over 2, and so forth. Yeah, there's an asymptote, but on its domain, it is. Log, same thing. Right? A log graph, continuous on its domain.
Continuous function. Is the continuous function imply constant?
Yes, it does. Yes, 100%. Unless an interval is specified. Yeah, actually, what Duke just said is very important. By default, when you're asked if something's continuous, the assumption on its domain form. But what's going to happen here, it's really going to be looking at piecewise functions. And that's where I'll deliberately make some discontinuities. So make sure you're stating these things. That's a totally different thing. But IVT, you have to have continuity for it to work.
So IVT based on this.
Yeah, we're not there yet. We'll do that on Wednesday. You're just getting ahead of me. Okay, have you guys seen this before? The greatest integer function. Yeah. Okay, good. Okay. Do you guys do that in this Wong's class? Okay, because I didn't teach you guys. I don't think I did. So, all right, it's a very simple function. Just so you know how it works. What would that equal? What's the greatest integer less than or equal to 1.5? 1. So you always choose the integer that's less than or equal. Like if I have 1.999, that's still 1. But then when I hit 2, guess what? Now it's 2. So it jumps. Sometimes it calls it a staircase or a step function. It looks like steps, right? Sometimes it calls it a step function. Or like a rounding function. You want to think of that rounds down, I guess. So is this continuous? No. The domain is all real numbers still, right? So it's a continuous function? No. And that's because the limit does not exist at each integer value of x. It's defined there, but condition 2 fails. And of course, condition 3 fails too. Because without condition 2, you can't do condition 3. Okay, without sketching, determine analytically whether this is continuous. So you're going to do the LHL and the RHL. LHL is going to be this: limit as x approaches 1 from the left side. That'll be 2 times 1 squared, which is 2. RHL. So in this case, we're going to say yes. gonna say yes. Because f of 1 exists, right? Part of our domain. The limit as x approaches 1 of f of x exists. And lastly, f of 1 equals the limit. Sorry, I'm kind of tucking this in here. Is a true statement. That's why. Yeah.
There was just just that.
Great question. Yes, and you're correct. So what if I just had this, right? And then what if I had something like weird, like well, not weird, but like say I had this here. So f of x equals 4 at x equals 1. So now the point's floating. So what's going to happen?
Then you're gonna have something kind of like this. That's gonna be kind of like a parabola, right? Wait, I messed that one up. We did that. Hold on. Oh, here we go. Yeah, you have this, and also you have like something kind of like this, and you have a point floating. So if I did that, if I decided to doctor out this piecewise function
Where the greater than or equal to next to 5x minus 2 is just greater than. And then I added a third thing. Hey, fx equals 4 x equals 1. Now I got to remove all this continuity. Hence, continuity fails. Condition 1 pass, condition 2 passes, condition 3 does not pass. So we went 1, 2, boom, boom. Oh no, condition doesn't work. Can't do it. So great question. I'm glad you brought that up. That might be a test question. Actually, I like it now. Thanks, Carl, for making me a test question. No, I got some juicy ones I'm going to come up with. So I'll make sure you guys get practice though. I'll make sure you get enough practice. So. This one is, yes. But I just came up with a different scenario. According to Carlson. This one is, yes. And that's that. Okay, I don't want to go any further. I'll stop there. So homework will be the rest of handout B. So 11th, piecewise, more piecewise, absolute value, radical stuff. And then just section A. Actually, can we? No, oh shoot, we can't do this one. We can't do it. Damn it. Sorry. Shouldn't have swore. Man, yeah, we can't do it. Had this great discussion on continuity and it really hold on a sec here. Okay, so your homework will be actually even lighter. Maybe see handout. No, we're not ready to do that one yet. There's another handout C. Oh no. I'm not ready to do that yet. Okay. So most likely what will happen is that I'll wrap up. I'll do part 3. The homework will be kind of meaty. So yes, there's some homework over break. I'm sorry. We need to do that. So yes, I know it's kind of, I know. But homework will be pretty light. Just 11 through 17, guys. That's all. You guys can knock it out. Probably can knock it out now. So. All right.